Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to present to you some key concepts of linear algebra as a preparation for exams. And the first concept that we are going to see is matrix multiplication. In linear algebra, matrices represent transformations on vectors. You are going to somehow modify a vector. Let this 3 by 3 matrix represent a transformation. We're calling here transformation A. And let this 3 by 3 matrix represent another transformation, and we're calling it transformation B. What we want to compute is matrix C, which is going to represent the composite transformation that A and B perform separately. A performs one task, B performs a different task. We want C to perform at once what A and B perform separately. And to do this, we need to multiply them. Okay? Let's take a look at the general term Cij. I represents the ith row of the first matrix, and J represents the jth column of the second matrix. Okay? Knowing this, we can multiply matrices. Let's go first to C11. C11 is going to be obtained from the multiplication of row 1 of the first matrix and column 1 of the second matrix. Okay? We multiply then this A11 times B11, A11 times B11 plus A12 times B21, A12 times B21 plus A13 times B31, A13 times B31. Okay? And with this calculation, we find the C11. Let's go to C12. C12 is going to be obtained from the multiplication of row 1 of the first matrix and column 2 of the second matrix. A11 times B12, A12 times B22, A13 times B32. C13 now. C13 is going to be obtained from the multiplication of the first row of the first matrix and the third column of the second matrix. A11 times B13 plus A12 times B23 plus A13 times B33. Okay? I am going to leave this. I'm going to leave this for you to try yourself, and we are going to work on these guys here, okay? Let's do for C31. C31 is going to come from the multiplication of the third row of the first matrix by the first column of the second matrix. A31 times B11 plus A32 times B21 plus A33 times B31. Okay, let's do it for this element now. C32. C32 is going to be obtained from the multiplication of the third row of the first matrix and the second column of the second matrix. A31 times B12 plus A32 times B22 plus A33 times B32. And the last, C33, is going to be obtained from the multiplication of the third row of the first matrix and the third column of the second matrix. A31 times B13 plus A32 times B23 A33 times B33. Okay, this is the way we carry out matrix multiplication, and I told you the purpose. We have different transformations, and we decided that we want them to be done at once instead of separately. Then we compute the matrix that carries out these two transformations at once instead of separately like this. Okay, this is the first topic, matrix multiplication. Let's go to the second topic. Let's go to topic number 2, determinants. Frequently in linear algebra, the problem consists of finding the solution of a set of linear equations. If the determinant of the matrix that represents the system is different than 0, the matrix has a non-zero determinant, we conclude that the system is consistent, okay? It has a possible solution. Then, if you calculate the determinant of a matrix and you find that this determinant is non-zero, then you know that the system is consistent and thus has a solution. Alright, let's go first and see the determinant of matrices of order 2. Let A be the matrix okay, the determinant of such a matrix is going to be the multiplication of these elements minus the multiplication of these elements. Okay? This is the determinant of a matrix of order 2. If this is non-zero, then you know that the system that this matrix represents is consistent. It has a solution. Now let's inspect the determinant of matrices of order 3. Let A now be this matrix here. We want to calculate the determinant of this matrix. To do this, frequently we apply the rule of Sahir. The rule of Sahir is simple. The rule of Sahir is this. We repeat these two columns here. And we follow the multiplication guided by these arrows here. Okay? Knowing that for these guys, the multiplication of the elements has to be multiplied in the end by -1. And for these guys here, you keep the original sign. Okay? Then the rule of Sahir says that the determinant of A is going to be -1 times the multiplication between these elements here, A31 times A22 times A13 plus the multiplication between these elements, A32 times A23 times A11 plus the multiplication between these elements, A33 times A21 times A12. Okay? And the positive side plus A11, A12, A11, A22, A33. Plus A12, A23, A31, plus A13 times A21 times A32. Okay? This is the rule of Sahir. And if the determinant is non-zero, then we know that the system that this matrix represents is consistent and thus has a possible solution. Okay? Now, let's consider the determinant of matrices of order greater than 3. Let's use an example. Let's use this matrix here. 2, 4, 1, and 0. 3, -2, -5, and 3. -1, 1, 2, and -2. 0, 3, 1, and 6. To calculate the determinant of a 4x4 matrix, we need to use the following algorithm. The determinant of a matrix of order higher than 3 is going to be calculated from j equal to 1 or I equal to 1 to n. You can choose columns or rows, okay, depending on your selection. For example, I could choose the first column, I could choose the first row to reduce the matrix. You're gonna see how it is done. And we are going to use a general term here, multiplying a cofactor. This capital A here is called a cofactor. And this small a, aij here, is a random element here, okay, general term, and this is called a cofactor. And what is a cofactor? The cofactor aij is equal to -1 raised to the power of I plus j times the determinant of a matrix that you obtain by removing row I from the original matrix and column j from the original matrix. Okay? So this is a cofactor, and you are going to use this cofactor here for every one of the elements of the row or the column that you choose. Okay? I will advise you here, and not just me, but every teacher would advise you to choose a row or a column with most zeros. We have a 0 here and we have a 0 here. So let's choose the first row. This is going to be our guide. We are going to use the first row as our guide. So the determinant of this 4x4 matrix is equal to A11 times the cofactor A11 plus A12 times the cofactor A12 plus A13 times the cofactor A13 plus A14 times the cofactor 14. Okay? You can see that we do not need to worry about this multiplication here because A14 is 0. You see here that A14 is 0. Then we can cancel this, okay? That's why we advise you choose columns or rows with most zeros, because you can eliminate easily. Alright? Okay. Now the determinant is going to be A11 is 2, A12 is 3, A13 is -1. Okay? Then the determinant of this matrix here is going to be 2 times the cofactor A11 plus 3 times the cofactor A12 minus 1 time the cofactor A13. Okay? We can erase this one and simply leave the negative sign. Alright, so let's calculate the cofactors. Cofactor A11 is -1 times 1 plus 1, okay? 1 plus 1. And we remove the first row and the first column of the original matrix. We remove the first row and the first column of the original matrix. -2, 1 and 3, -5, 2 and 1, 3, -2 and 6. Okay? So the cofactor is going to be -1 squared is 1, +1. Then it is going to be simply the determinant of this matrix here. You calculate the determinant of this 3 by 3 matrix, and the determinant of this 3 by 3 matrix is the cofactor. And you simply put it here. Okay? Now let's go to this cofactor here. A12 is going to be -1 raised to the power of 1 plus 2. And we are going to remove from the original matrix the first row and the second column. Okay? Then it is going to be 4, 1 and 0, 1, 2 and -2, 3, 1 and 6. Okay? -1 cubed is -1. So you are going to calculate the determinant of this matrix. And multiply the determinant by -1. And the last cofactor is A13, which is -1 raised to the power of 1 plus 3. And we are going to remove from the original matrix row 1 and the third column. Row 1 and the third column, and the cofactor is 4, 1, 0, -2, -5 and 3, 3, 1 and 6. Okay, -1 to the fourth is +1. Then you simply calculate this determinant here. 4, 1, 0, -2, -5 and 3, 3, 1 and 6. And then you put these values that you obtain from the determinants and put them here. And you are going to ultimately find that the determinant of this 4 by 4 matrix is 13. You apply rule of Sahir here, here and here, and you multiply this by -1 here, this by 3 and this by 2, and you find 13. Okay? This is all for determinants. Let's go now to the third topic. Topic number 3, matrix inversion. Given this matrix, matrix A, state whether A is invertible or not. And if yes, find its inverse. Alright, my friends, this is the exercise that we are going to solve to demonstrate how to invert a matrix. But before, we need to know if the matrix is invertible or not. And how do we know whether a matrix is invertible or not? The determinant if the determinant of the matrix is non-zero, then it is invertible. Otherwise, it is not. Okay? By applying the rule of Sarri here, okay, we've studied the determinants. By applying the rule of Sarri, we found that the determinant of A is equal to negative 15. Okay? You may find a negative number here or a positive number. It doesn't matter. What matters the most is that it is non-zero and it grants that the matrix is invertible. Alright, and now let's find the inverse matrix of this matrix here. Alright, the determinant of A is different than 0, it is invertible. To find the inverse matrix, use the identity matrix as follows. I'm going to show you how to use the identity matrix to come up with the inverse matrix of any given matrix whose determinant is non-zero. Okay? Let's rewrite this matrix here. And beside it, we are going to write the identity matrix. Okay? We are going to operate on the rows of the original matrix until we find the identity matrix here at the left side. What's going to come up, what's going to pop up at the right side will be the inverse of the matrix. Alright? So let's operate on the rows of this matrix here. We can firstly multiply R2 by negative 1. Okay? We are going to multiply R2 by negative 1 and put it in the place of the old R2. Okay, by R2 I mean row 2. We are going to multiply row 2 by negative 1 and substitute it in the place of the old row 2. And subsequently we are going to swap row 2 with row 1. And in this way, the new matrix becomes you see that we are altering the identity matrix. We had the identity matrix here, we are altering it. Okay? Our objective is to make the identity matrix appear here, and what's going to pop up at the other side is the inverse of the original matrix. And subsequently, we are going to perform the following operations on the rows of this matrix here. We are going to row 2 minus 3 row 1 and substitute this in row 2. And row 3 minus 4 row 1 and substitute this in row 3. Okay? And in this way, our new matrix becomes What else can we do? What else can we do? Observe that the identity matrix is appearing here, okay? We have one here, leading this column, and below it, only zeros. We have already a 0 here, and we want to make appear a 0 here, and only this one shall exist in this column here. And in the place of 7, it is our objective. We want to make appear a 1 here, and in the place of -3 and 11, we want to make appear 0. And this is our objective. This is what we are going to do. And to further simplify this, we are going to row 3 minus 2 row 2 in the place of row 3, and 1 over 15 times R3 in the place of R3. Okay? And we are going to continue doing these operations here until we have this matrix here, which is the inverse of the original matrix. Okay, it is going to be, the inverse matrix is going to be 1 over 15, 6, -7 and 2, -9, 23 and 2, -3, 11, and -1. Okay? The idea behind matrix inversion is to firstly understand whether the matrix is invertible or not. If the determinant is different than 0, the matrix has a non-zero determinant, it is invertible, otherwise it is not. Provided that the matrix is invertible, we are going to put it in this form here, with the identity matrix at the right side, and we are going to operate on the rows of the original matrix until we make the identity matrix appear here. We want to make the identity matrix 1, 0, 0, 0, 1, 0, and 0, 0, 1. We want to make the identity matrix appear here, and what is left at the right side is the inverse of the original matrix. And for this matrix here, this is the inverse matrix. Okay, this is the idea behind matrix inversion. Okay, my friends, this is all for topic number 3. Let's go to topic number 4. Topic number 4, determine if the system is consistent. And what does it mean for a system to be consistent? A consistent system has at least one solution. What does it mean? It means that there is at least one triplet of values x, y, and z that satisfies simultaneously these 3 equations, okay? And to determine whether this system here is consistent or not, we are going to operate on the rows of the augmented matrix, okay? The augmented matrix is this is the augmented matrix that represents this system here. We are going to operate on the rows of the augmented matrix to determine whether the system is consistent or not, if there is a solution to this system, okay? A triplet of x, y, and z that simultaneously satisfies these three equations. Okay, the first operation will be to swap row 1 with row 2. Okay, row 1 and row 2. We are going to simply swap them, and subsequently we are going to conduct the following operation. Negative 5 halves times row 1 plus row 3, and we are going to substitute this resulting row 3. And after doing this, we get the following matrix. Okay? And to finish, we are going to carry out these operations in half a row 2 plus row 3 and substituting row 3. And we find the matrix, the result. And this is the matrix that is left off from the operation on the rows of the augmented matrix. And if we take the determinant of this matrix here, we discover that this determinant is equal to 0. If you apply the rule of Sahir here, you're going to discover that this determinant is equal to 0. And what does it mean? It means that the system is inconsistent. Okay? The system is inconsistent. Whenever the determinant of the matrix, of this matrix here, or any other matrix that results from the operations on the augmented matrix, if you observe that the determinant of the matrix is equal to 0, the system is inconsistent. Had the determinant of this matrix being different than 0, then the system would be classified as consistent. Okay, a consistent system has a triplet of values x, y, and z that satisfy simultaneously the equations. Okay, this is everything for topic number 4. Let's go to topic number 5. Exercise number 5. For what values of h and k is the following system consistent? Okay, we need to determine whether the system is consistent, and for what values of h and k the system will be consistent. All right, we are going to use the following operation to determine if the system is consistent or not. We are going to multiply the first equation by 2 and sum with the second. Okay, 4x minus 2y equal to 2h, and negative 4x plus 2y equal to k. Alright, and if we sum these two equations, we get that 2h plus k is equal to 0. And what does it mean? It means that the system is consistent for values of h and k such that 2h is equal to k. In other words, k is equal to negative 2h. The system will be consistent for any value of k and h such that k is equal to negative 2h. Let's choose any. Let's choose any. For example, if k is equal to 100, for example, then h, 2h plus 100 is equal to 0. 2h is equal to negative 100, h is equal to negative 50. Then if k is equal to 100 and h is equal to negative 50, then this system will be consistent. Okay? You can choose any kind of value provided that k is equal to negative 2h. Alright, this is all for exercise number 5. Let's go to exercise number 6. Exercise number 6. Write a system of equations that represent or is similar to this vector equation. Okay, it is simple, it is easy. I have here x multiplying a vector plus y multiplying a vector, and the result is also a vector. We want to write a system of equations that is equal or similar and represent this vector equation here. It is very simple. Just to exercise, you can say that x plus y minus 2y, 3y is equal to 1, negative 2, and 1. And then you can simply write that it is equal to x plus y equal to 1, x minus 2y equal to negative 2, x plus 3y is equal to 1. Okay, so this is the system of linear equations that comes from this vector equation. They are similar and they represent the same process, or if you prefer, the same transformation, the same system. Okay, this is all for topic number 6. Let's go to topic number 7. Exercise number 7. Given these vectors, vector a1, vector a2, vector a3, and vector b, determine whether vector b is a linear combination of vectors a1, a2, and a3. Okay, this is what we are going to do. We are going to try to prove whether b is indeed or not a linear combination of the vectors a1, a2, and a3. If vector b is a linear combination of vectors a1, a2, and a3, then we can write it in this fashion: x a1 plus y a2 plus z a3 equal to b. Okay? This is the very definition of a linear combination. If b is a linear combination of vectors a1, a2, and a3, then vector b can be written in this way: x a1 plus y a2 plus z a3. All right? And we are combining, this is linear combination, we are combining the vectors, and the result must be the vector b. And there will be only one triplet of values, x, y, and z, that will produce b. Okay? Alright, so let's look for these values of x, y, and z that produce b. In this way, we can write it in this way here. X 1 negative 3 0 plus y 0 negative 3 and 2 plus z 5 negative 1 and 5 equal to b, where b is going to be written as 2 negative 1 and 5. Okay, this is the vector equation that we shall solve, and we can attempt to solve it in this format, or we can use a system. All right, we can rewrite it in this way. It is possible to rewrite this in this way. We line up the columns and this matrix multiplication must produce alright, which is similar to the system, and the system is x plus 0 y plus 5z equal to 2, 3x minus 3y minus z is equal to negative 1, and 0x plus 2y plus 5z equal to 5. Okay, this matrix multiplication or this vector equation is similar to this system here. Okay, and if this system is consistent, there is at least one solution, then indeed B can be written as a linear combination of this vector here. Otherwise, it cannot. B cannot be written as a linear combination of vectors A1, A2, and A3. We are going to use the augmented matrix to determine whether the system is consistent. The augmented matrix is okay, we are going to operate on the rows of the augmented matrix. And when we do this, okay, you need to attempt to create here a matrix that is going to allow you find a value for x, a value for I, and a value for z. All right, and ultimately you're going to find this 1 0 and 0, 0 1 and 0, 0 0 and 1, multiplying x, y, and z, and here 1 over 43, 211, 405, 25. Okay, so what does it mean? It means that the system is consistent. It means that there is a solution. X, observe here, x is equal to 1 over 40, 3 times 211. Observe here that y is equal to 143 times 405. And observe here that z is equal to 143 times 25. Okay, this is the solution. Okay, x, y, and z, are equal to 211 over 43, 405 over 43, and 25 over 43. Okay? And the system is consistent. There is a possible solution. And it means ultimately, this is the conclusion that we wanted to arrive at, is that B is indeed a linear combination of A1, A2, and A3, okay? And this is all for topic number 7. Let's go to topic number 8 now. Topic number 8, let A1 be this vector, and A2 be this vector here, and we want to determine the values of H that make the vector B in the span of A1 and A2. Alright, for what values of H is B in the plane spanned by A1 and A2? Let's go to the solution. B is in the span of A1 and A2 if it can be written as a linear combination of A1 and A2, such as XA1 plus YA2 equal to B. Alright? You see that if B can be produced by combining A1 with A2 in accordance with the laws of linear algebra, not geometric algebra or any other kind of algebra, non-linear, you'd say non-linear algebra, we are going to use the laws of linear algebra to combine A1 and A2 and produce B. If B can be produced by combining linearly A1 and A2, then B is in the span of A1 and A2, and we want to find values of H that cause it to happen, that make it possible, okay? And we are going to write this matrix equation in this way. Okay, we are looking for values of H that make this linear combination possible, and we are going to use the augmented matrix. The augmented matrix is and we need to operate on the rows of the augmented matrix. And if we do this, operating on the rows of the augmented matrix, we find this. Okay, and what is the conclusion? The conclusion is that H plus 17 has to be equal to 0. That is, H has to be equal to negative 17. And when H is equal to negative 17, B is indeed in the span of A1 and A2, okay? This is the solution of exercise 8. Let's go to exercise 9. Topic number 9. If matrix A is composed of these two vectors, vectors A1 and A2, where A1 is this vector and A2 is this vector, determine whether the vector U is in the plane spanned by the columns of A. We want to assess whether the vector u is spanned by the columns of A, okay? Vectors A1 and A2. And let's go to the solution. The solution will be vector u is in the plane spanned by the columns of A if and only if u is a linear combination of the columns of A. In other words, u will be in the span of A1 and A2 if it can be written as a linear combination of A1 and A2. Okay? Then x 3, negative 2 and 1 plus y negative 5, 6 and 1 equal to 0, 4 and 4. Okay? We are combining linearly A1 and A2 and see whether this linear combination produce u. If u can be produced by this linear combination here, then we can state confidently that it is in the span of A1 and A2. Okay? Okay, and let's use the augmented matrix to determine whether this is possible, if this system is consistent. If there is indeed this solution, we are going to operate on the rows of the augmented matrix. And by operating on the rows of the augmented matrix, we find this. Here, we can rewrite this in this way here. And we find that 8y is equal to 12, which means that y is equal to 3/2. And by inspecting this product here, we find that x is equal to 5/2. Okay? And we found a solution for this x and y that make u. And the result, the conclusion is that indeed u lies in the span of A1 and A2. Okay? As this equation has a solution, we will discover that u indeed is in the plane of the columns of the plane spanned by the columns of A. And this is all for topic 9. Let's go now to topic 10. Exercise number 10. Let V1, V2 and V3 be R3 vectors And the exercise asks us, letter A, determine if the set V1, V2, and V3 is linearly independent. Letter B, if possible, find a linear dependence relation among V1, V2, and V3. Okay? These are the questions. Let's go to the solution. In letter A, we must determine if there is a non-trivial solution of the following equation. This vector equation here. We must determine whether there is a non-trivial solution to this vector equation. What is, first of all, what is the trivial solution? The trivial solution is when x, y, and z are 0, but we are not interested in this solution. We want a non-trivial solution to this vector equation, okay? And to find this non-trivial solution, we will need to use the augmented matrix. The augmented matrix will be and we will operate on the rows of this augmented matrix. And we can add, subtract the rows, and after doing this, we discover this equation here, this augmented matrix here. And what does it tell us? It tells us that x and y are basic variables, while z is free. Z can assume any kind of value, while x and y are basic variables. Each non-zero value of z determines a non-trivial solution. Okay, so for each non-zero value of z, we have a non-trivial solution to this equation. And by inspecting this, we discover that they are, the vectors v1, v2, and v3, they are linearly dependent. They are not linearly independent. They are linearly dependent. And what does it mean? It means that one of them can be written as a linear combination of the others. That's why they are linearly dependent. And to demonstrate this, observe that 2 times v1 plus v3 is equal to v2. Okay? Let's inspect this and see whether they are linearly dependent or linearly independent. If one of them, v1, v2, or v3 can be written as a linear combination of the others, then this set here is linearly dependent. And we will assess whether this combination here, 2 times v1 plus v3, does produce v2. Okay? So 2 times v1 plus v3 equal to v2. Okay? 2 times 1 is 2, plus 2 is 4. 2 times 2 is 4, plus 1 is 5. 2 times 3 is 6, plus 0 is 6. Okay? Then V2 can be written as a linear combination of V1 and V3. Alright? So if x is equal to 2, y is equal to 1, and z equal to 1, we have proved that there is this triplet here, that makes this, okay? Alright, we can, here z is negative 1 because for z equal to negative 1, alright? 2 times this plus 1 times, okay, no. Let's understand it a little bit more. You're gonna see that for x, here x equal to 2, for y is connected to V2, so for y equal to negative 1, and z equal to 1, then for these values here, we can produce a 0 here, alright? The non-trivial solution, okay? So there is a non-trivial solution, and this is an example of this, okay? So the ultimate conclusion is that the vectors are linearly dependent, alright? One of them can be written as a linear combination of the others. Alright, this is all for exercise 10. Let's go to exercise 11 then. Exercise 11, determine if the vector set V1, V2, and V3 are linearly dependent. Okay, the objective is to see whether they are linearly dependent. And how do we know that they are linearly dependent? The vectors are linearly independent if and only if they can be written as a linear combination of the others. So if there is one of them that can be written as a linear combination of the others, then they are linearly dependent. Otherwise, they are linearly independent. Okay? So let's inspect this vector equation. X v1 plus y v2 plus z v3 equal to 0. Okay? In other words, x 500 plus y 7 to negative 6 plus z 9 for negative 8 equal to 0, 0, 0. If and only if x equal to y equal to z equal to 0 produce the vector 0, then they are linearly independent. However, if there is any kind of a number, x equal to one number, and y equal to another number, and z equal to another number, and if there is any non-zero number that you can put in the place of x, y, or z that cause this matrix, this vector equation to be equal to 0, then they are linearly dependent. Okay? This is the idea behind linearly independence or linearly dependence. The vector set is linearly independent only if this is true. Otherwise, they are linearly dependent. Okay? Let's inspect the augmented matrix and see if we can find a relation that is better for us to visualize if they are linearly dependent or linearly independent. Okay, the augmented matrix is this is the augmented matrix, and if we operate on the rows of this augmented matrix, we find all right. Observe here, observe this row here. This row is 0x plus 0y plus z equal to 0. All right? The only possibility for this equation to be equal to 0 is when z is equal to 0. Otherwise, this is not true. Any kind of a number in the place of z, for example, z equal to 15, is going to be different than 0, and then it makes this equation wrong. It is not true, it is false. 15 is not 0. Okay, so the only possibility for this equation here, the third row of this matrix, to be equal to 0 is when z is equal to 0. And let's inspect this row here. Let's inspect this row here. 0x plus y plus 2z equal to 0. Okay, if z is already here, 0, we have already stipulated that z has to be equal to 0. The only possibility then for this equation here becomes 0 is to have y equal to 0 here. Okay? Therefore, the only possible solution is the trivial solution. X, y, z equal to 0, 0, 0. The only possible solution is the trivial solution. Only when x, y, and z are all 0, this vector equation here becomes 0. And what is the conclusion that we have here from this is that indeed they are linearly independent. They are linearly independent. They will be linearly independent only when the trivial solution is the solution of this vector equation here. If there was a non-trivial solution, then we could confidently say that they are linearly dependent, okay? One of the vectors could be written as a linear combination of the others. However, as we discovered that the only possibility is when x, y, and z are 0, then we have come up with the conclusion, where we have achieved the conclusion that the only possible way is this, and then it makes them linearly independent. Okay, this is all for exercise 11. Let's go to exercise 12. Exercise 12 now. Let A be this matrix that represents a transformation. U, B, and C these vectors, and define a transformation of a vector belonging to the R2 set of numbers, and we want to transform this into a vector of the R3 set of numbers. And in letter A, the exercise asks us to find T of U, the image of U under the transformation T. In letter B, find an X, a vector X in R2 whose image under T is precisely B. And in letter C, is there more than one vector X whose image under T is B? Okay? And letter D, determine if vector C is in the range of transformation T. Okay, this is what we are going to do for exercise 12. Letter A. A is the matrix that represents the transformation, okay? We apply the transformation to the vector and we get the transformed vector, the vector after applying the transformation. And we want to assess whether T of U, the image of U under the transformation. We want to find the transformation applied at vector U. Okay, there are two ways of doing this. We can simply do this. We can simply apply the transformation 1, 3, -1, -3, 5, and 7. We can apply this transformation to vector U, 2 and -1, and then we simply multiply here, and there is also the possibility of using this. We simply use the coordinates of vector U. Where there is x1, we put 2. Where there is x2, we put -1. And then we find the vector 5, 1, and -9. All right? This is the image. This is the image. Transformations are functions. Okay? What enters in a function is the input. And what goes out is the output. The output is also called the image. And U is the input, and the image is what comes out, the output of the transformation. Let's go to letter B. Letter B, we want to find an X, okay, a domain, a member of the domain, whose image is B, okay? We want the image to be B, okay? And we want this, we are going to apply the transformation to a vector, any kind of vector. We are going to use a random vector here. We are going to call here X and Y. And what needs to be produced in this transformation is vector B. Vector B is the image. Okay, we want to find this vector here that produces B. Okay, there are several ways of doing this. Okay, you can invert. We cannot invert this matrix because it is not a square matrix. Okay, we are going to have to use another strategy. Had this been a square matrix, we could simply invert the matrix, and then it would be easier computationally, but as this is not a square matrix, we are going to need to use a different strategy. We are going to multiply the transformation by the vector, and then we find this x minus 3y, 3x plus 5y, negative x plus 7y. Okay, so this is equal to this, and to find the values of x and y that satisfy this, we will work on the augmented matrix. The augmented matrix will be 1, 3, -1, -3, 5 and 7, and 3, 2, -5. Okay, we are going to operate on the rows of the augmented matrix, and after operating on the rows of the augmented matrix, we find this matrix here. Okay, after operating on the rows of the augmented matrix, we find this. All right, and what does it mean? It means that x is equal to 1.5 and y is equal to -0.5. Okay, then when x is 1.5 and y is -0.5, we have a vector. One vector. If we apply this transformation to this vector, we find the image, okay? What the transformation outputs when this is the input. All right, and this is all for letter B. Let's go now to letter C. What letter C wants? Letter C wants us to find another vector of the domain that produces B, and we have found that only this vector here, 1.5 and -0.5, satisfies. Had we found something different here, okay, there would be the possibility of other vectors producing B as image. Okay, let's go to letter D. What does letter D want? Letter D wants us to determine if C, we are going to work with C now, determine if C is in the range of transformation. Okay, so what does it mean? To be in the range of the transformation, what does it mean? Vector C is in the range of the transformation if C is the image of any kind of vector. All right? This is what being in the range of a transformation means. Okay? If C is in the range of this transformation, this is the idea behind the range. If C is in the range of this transformation, it means that we can use, if we apply this transformation to any kind of vector of the domain, C is going to pop up at the output, okay? And this is what we wish to find for letter D. If there is one vector, we're going to call it vector X. If there is a vector X, if we apply the transformation to vector X and we produce C, then C is in the range of the transformation, okay? And this is what we're going to do. We are going to apply the transformation. We are going to apply the transformation to a random vector. We can call it again X and Y. We could call it W and Z, but let's call it simply X and Y. And upon applying the transformation to this vector, C needs to be produced. Okay, operating on the rows of the augmented matrix, the augmented matrix is going to be this is the augmented matrix, and if we operate on the rows of the augmented matrix, we find this here. We find this. And what does it mean? It means that x 1 0 0 plus y negative 3 1 1 equal to 3 negative half and 2. From this, we find that y is equal to negative 1 half and y is equal to 2 at the same time. And it is not possible, and our verdict is that the system is inconsistent. If the system is inconsistent, we discover that the C does not belong to the range of the transformation. C is not in the range of the transformation, and this is all for exercise 12. Let's go to exercise 13. Exercise 13, consider the letter L of the figure made up of the vectors v1 and v2. Question: show the effect of the linear transformation, this linear transformation, on the L. Okay, we want to apply the linear transformation on this L here and see what happens. Okay, let's go to the solution. First of all, we are going to apply the transformation on v1, vector 1. Okay, so t of v1 will be equal to 0, 1, negative 1, 0, 1, 0, and we can simply multiply this matrix by this vector and we get this vector here. Now let's apply the same transformation to vector v2. If we multiply this, in other words, if we apply this transformation to this vector, we get, okay, and what does it mean? It means that they are going to be in this position here, okay. All right, here is 0, 1, and here is negative 2 and 0. What happened? We apply the transformation and this becomes this. What happened? The L is rotated, okay? The linear transformation rotates the L. The L is rotated by positive 90 degrees in the counterclockwise direction. This is the effect of the transformation, and this is all for exercise 13. Let's go to exercise 14 now. Exercise 14, find the standard matrix A for the dilatation transformation T of vector x equal to 3 times x. Alright, this is what we want. We want to find the matrix that represents this transformation here. Okay, and let's work with vector u. Okay, the vector that we are going to work with, A11, A21. Okay, this is the vector that we are going to work with. And the output needs to be vector v equal to 3 times A11 and 3 times A21, okay? Because this is the idea behind the transformation here. The transformation is going to extend the vector, to cause a dilatation to the vector. In other words, it's going to scale the vector by the factor of 3. This is what the transformation needs to do. Alright, so we are going to find we need a matrix that will represent the transformation on U, and will produce vector V, which is a scaled up version of vector U. Okay, so the matrix, we are going to call it B11, B12, B21, B22. On the transformation will be on A11, A21, and this will produce 3 times A11, A21. Okay, this is the idea of this transformation, to scale up the vector by a factor of 3. And if we carry out this multiplication here, okay, it is simple. If we carry out this transformation, we find that B11 times A11 plus B12 times A21 is equal to 3A11, okay? We multiply this by this, this with this, this with this, and it is equal to this. Now this with this and this with this will be equal to this. B21 times A11 plus B22 times A21 equal to 3 times A21. Alright? And by doing this, we discover that B11 is equal to 3, B12 is equal to 0, B22 is equal to 3, and B21 equal to 0. And then the matrix that represents this transformation is 3003, okay? This is the matrix that scales up the vector, the input vector, by 3, and outputs a vector that is obviously 3 times the input vector. Okay, this is all for exercise 14. Let's go to exercise 15. To finish our review, let's discuss eigenvectors and eigenvalues. Okay, what is an eigenvector? An eigenvector of a matrix is a non-zero vector such that AX is equal to lambda x, okay? If the transformation only scales up a vector by a number called eigenvalue, then this vector is an eigenvector of the transformation or of the matrix, okay? So we are applying the transformation to a vector. And this is the same, is similar to simply multiplying the vector by a number. Whenever this transformation is equal to the multiplication or to scaling a vector, x is an eigenvector of the transformation and the lambda is an eigenvalue of the transformation, okay? So this is the definition, the concepts behind eigenvalues and eigenvectors. Now let's go to exercise 15. Let A be this matrix here. Okay, let A be this matrix. U be this vector, and V be this vector here. Are U and V eigenvectors of A? This is question 15. Okay, so we are going to use this definition here to see if U or V or both are eigenvectors of A, okay? So we need to apply the transformation to the vector. 3, -2, -2, 3. We are going to apply the transformation to the vector. Okay? And by applying the transformation to the vector, we discover this vector here. -5 and 5. And this vector here is equal to 5 times vector U, not vector V, sorry, vector U. Okay? And what does it mean? It means that yes, indeed, U is an eigenvector of this transformation here, and the scaling up factor, the eigenvalue is lambda equal to 5. So U is the eigenvector and 5 is the eigenvalue associated with this eigenvector here. And now let's go and apply the transformation to this vector here. Okay, and we find that it is equal to 4 and -1. And this is not equal to any kind of lambda multiplying 2 and 1. Okay, so there is no lambda, there is no number, there is no scalar that we can multiply the vector by and find V. So V is not an eigenvector of the transformation. And our conclusion is that U is an eigenvector of A corresponding to the eigenvalue lambda equal to 0, and V is not an eigenvector of A because there is no lambda that we can use to multiply the vector and find the outcome of the transformation. Okay, so this is what we find in exercise 15. Let's go to exercise 16 and use more of the definitions related to eigenvalues and eigenvectors. Exercise 16, the last exercise of the series related to linear algebra, a review for exams. Let A be this matrix here, A equal to 7, 2, negative 15, and negative 4. Find the eigenvalues of A. We want to find the eigenvalues of A. And how do we find the eigenvalues of any kind of matrix? Okay, we are going to use this expression here. The determinant of A minus lambda I has to be equal to 0. Okay, this is the expression that we use to calculate the eigenvalues of a matrix. Okay, first of all, let's calculate A minus lambda I, and this will be 7 to negative 15, negative 4, minus lambda, multiplying the identity matrix, and we discover this matrix here, A minus lambda I equal to 7 minus lambda to negative 15, negative 4 minus lambda. Okay, this is the matrix. We need to find the determinant of this matrix here, and we are going to simply do this, and we are going to multiply here and here. The determinant is going to then be the determinant of A minus lambda I is going to then be equal to 7 minus lambda, negative 4 minus lambda. Okay, and this plus 13, plus 30, plus 30, plus 30. We have this product here, and we have this product here. Okay, so the determinant is going to be lambda squared minus 3 lambda plus 2 equal to 0. Equal to 0, where lambda, we're going to find two values for lambda, lambda 1, lambda 2. You can, of course, you can find yourself the roots of this quadratic equation here, and we find 2 and 1. Okay, and these are the eigenvalues of this transformation here. Okay, these are 2 and 1 are the eigenvalues of this transformation here. Okay, this is the video that I wanted to make, my friends, to talk to you about linear algebra and review together the concepts and solve some exercises that we need for our exams, whether public, if you want to be a civil servant, or if you want to participate in an exam for a private company, any kind of company that will apply exams for the entrance exams of these companies, or if you want to work for the government of your country, your city, your state, your county, You need to review these concepts to pass the exam, okay? And this is the idea behind these videos, to go over the topics, to review for exams. Alright, I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye.